All right, let's talk about the impacts of having strong intermolecular forces and maybe make yourself a list, but definitely try to reason this out. So, the first one I'm going to talk about is boiling points. If you have a strong intermolecular force, those molecules are going to be held tight to one another. They're going to be very difficult for you to rip apart. And therefore, those types of particles that have strong forces are going to have very strong or high boiling points. The same thing goes with melting points. If you have very strong forces holding those particles together, they're not going to want to slide past one another and be ripped away from one another. So, strong forces will give you very high melting points. What about surface tension? If you have strong forces, the molecules on the surface of a material will be knit very tightly together. We're going to have a high tension on our surface, something that's very difficult to break through. So, strong intermolecular forces create high surface tensions. What about viscosity? Viscosity is the resistance to flow, the resistance to pouring, basically. So if you're going to pour one liquid past another, the liquid molecules have to slide past one another. If you have weak forces, those molecules slide very easy past one another. But if you have strong forces, it's very difficult for those molecules to slide past one another. So you're going to feel a lot of resistance when they flow. High intermolecular forces create great viscosity. All right, two more. What about volatility? So let's define volatility. Volatility, Tility, is the ability to evaporate. Okay, so if a particle or a substance is going to evaporate up, if it's going to evaporate, it's best if those forces are weak. Then it can leave one another. So if you have strong forces, that substance does not want to leave itself. It does not want to evaporate. So if it doesn't want to evaporate, it will have a low volatility. Oops, my went all blurry on you. Okay. And the last one's a little weird, vapor pressure. So let me try to explain what I mean by vapor pressure. Let's say you put a substance in a jar and then cap that jar. Put it in a container, kind of like a terrarium. If you had some water and some plants and you covered it with some glass, okay? Now, this substance that's in here inside this container, that substance might evaporate. And when it evaporates, the liquid turns into a vapor. We have a vapor. That vapor is going to be hitting the walls of this container. It will be exerting a pressure on that container. The more vapor you have in here, the more pressure will be inside this container. That is the vapor pressure. Well, what if this substance doesn't evaporate at all? If it's held together very, very strongly, it's not going to evaporate. We won't have a lot of vapor, and the pressure, the vapor pressure, will be very, very low in that case. All right, now I'm going to ask you a bunch of questions regarding these particular physical properties, these particular physical traits. I want you to go about these questions in two ways. The first thing I want you to do is ask yourself, are you looking for the stronger force or are you looking for the weaker force? Okay, then you need to identify the types of forces for each of those molecules. Okay, so let's go through some examples. All right, example number one. I'm going to ask you who has the higher boiling point between methane and octane. Okay, if I want a high boiling point, I am looking for the one that has the strongest intermolecular force, the one that's hard to rip apart. That's step one. Step two, I know I want the strongest force. Let's identify the forces of each of these. Each of these particles is made entirely of carbon and hydrogen. Therefore, they both have London dispersion forces. So CH4 has a London dispersion force. C8H18 has London dispersion forces. It looks like we're tied. However, one of those molecules has stronger London dispersion forces than the other. The way we can power up our London dispersion forces is by mass. The one with more mass, the bigger electron clouds, is going to have greater London dispersion forces. So the strongest one will be octane. And in fact, octane, gasoline, is a liquid. Methane is a gas that comes out of your Bunsen burners. All right, let's try another one. This question number 2 says, which of the following has the higher melting point? If you want a strong melting point, it's going to be very difficult to melt it, well, then you're looking for the molecule that has the strongest forces. Now we need to identify the forces. So let's start at the top. First question is, do we have H-phone? Well, let's draw it. We have oxygen attached to a hydrogen and a hydrogen. Yes, we have H attached to F, O, or N. So water is capable of hydrogen bonding, dipole-dipole, and London dispersion forces. Now let's take a look at H2S. If you take the time to write the Lewis structure for H2S, what you're going to see is that you have a molecule that looks just like water. This is a 1, 2, 3, 4, a tetrahedral molecule with 2 lone pairs. It is a polar molecule. Now we go down the list. Does this have H-phone, H-bonding? No. But being polar, it has dipole-dipole forces and London dispersion forces. I've identified the forces. Now, I wanted the strongest one. H-bonding dipole-dipole and LD versus dipole-dipole LD. H-bonding wins the hand. All right, let's try another one. Which one has the higher surface tension? If you have a lot of surface tension, you're going to be knit and held together very tightly on the surface of your liquid. So you're looking for the stronger of the intermolecular forces. Now we need to identify it. To identify it, we need to draw them. The Lewis structure for boron trifluoride looks like the following: BF3 with all the lone pairs on the fluorines. The Lewis structure for NF3, if you take the time to count your electrons, put the different one in the middle, fill the outsides, leftovers on the center, this is what nitrogen trifluoride looks like. Now, if we go to identify the forces, neither one of these have H, FO, or N, H-phone. We don't have hydrogen bonding. BF3, while it might look polar at first glance, will really go into a Mercedes sign trigonal planar arrangement. That is a non-polar arrangement. So for BF3, all we have is London dispersion forces. For NF3, this is a tetrahedral molecule with 4 domains, where one of them is a lone pair. That is a polar molecule. Therefore, nitrogen trifluoride has dipole-dipole and London dispersion forces. We want the strongest force. So we're going to choose not just London, but the one that has London and dipole-dipole forces with it. All right, let's try another. We want to know which one of these 2 molecules has the highest viscosity, the highest resistance to flow, does not want to run across each other, wants to stick, it's sticky. So high viscosity is going to be the one with the stronger force. Now, instead of drawing this one, however, we can shortcut it. Both of these molecules are all carbon and hydrogen. Therefore, I know that both of these molecules only have London dispersion forces with them. So for this particular one, it looks like a tie. If it's a tiebreaker we need, look to mass. We can make London dispersion forces stronger with mass. 8 carbons, 10 carbons, 10 carbons wins. So C10H22 is going to be our one with the highest viscosity. All right, next molecule. Which one of the following has the higher volatility? Remember, volatility is the ability of a substance to evaporate. If it's evaporating a lot, that's a weak force that's holding it together. So this time, I am looking for the molecule that has the weakest force. Now let's identify it. Do either of these have H attached to F, O, or N? Yes. HF, hydrogen fluoride, will experience H bonding, dipole-dipole, and London dispersion forces. HCl, on the other hand, is just a polar molecule. Chlorine wins the tug of war, pulls the electrons towards it. Since it is a polar molecule, it experiences dipole-dipole and London. I want the weaker one. London's dipole-dipole, H bonding wins, so the weaker one is HCl. All right, let's try a few more. I hope you're getting the hang of this. All right, next set of problems. I want the molecule with the highest surface tension. The highest surface tension is held together very strongly on the surface of the liquid. I am looking for the stronger of the two forces. First thing I notice when I look at this is I've got some carbons and hydrogens, but I end with an O and an H. They're trying to give me a clue that in my molecule, I have an OH alcohol group. An O and an H has H phone. Both of these are going to experience hydrogen bonding, dipole-dipole, and London dispersion forces. H bonding DD and LD. It looks like we have a tie. So whenever it looks like we have a tie, the tiebreaker is usually the London dispersion forces. They both have hydrogen bonding, dipole-dipole, but which one has stronger London dispersion forces? 1 carbon, 3 hydrogens, 5 carbons, 11 hydrogens. That is going to be my strongest force. That will have the highest surface tension. All right, next set. Who has the higher boiling point? If it doesn't boil easy, it's going to have a very high temperature to boil, a high boiling point. We're looking for the forces that are stronger. Now, if we go ahead and draw that, F2 is nonpolar, no one wins a tug of war. Br2 is nonpolar, no one wins a tug of war. Nonpolar molecules experience London dispersion forces. So it looks like we have a tiebreaker. So we need to see who has more mass, more electrons, fluorine or bromine. Bromine for the win. We wanted the stronger one. Bromine it is. All right. Next particular set. Let me get some more paper here. Is which one has a higher melting point? If we want a high melting point, we need to find the stronger of the two forces. Now, off the top of my head, I actually don't know the answer to this one. Actually, I think I do. KrF4, the Lewis structure, I was trying to remember what it is. The Lewis structure for KrF4 is 4 fluorines, 1, 2, 3, 4, with 2 lone pairs. For selenium tetrafluoride, it is also 4 fluorines, but this time there is only 1 lone pair. So we ask ourselves some questions. Do either one of these have H phone? No. Are they polar or not polar? Well, let's take a look. This first molecule has 1, 2, 3, 4, 5, 6 domains. 1 up, 1 down, 4 in a ring around the middle. 2 of those happen to be lone pairs. I'm going to lone pair top, lone pair bottom. This is a non-polar molecule. The only thing it experiences is London dispersion forces. Now, selenium tetrafluoride, on the other hand, has 1, 2, 3, 4, 5 electron domains, 1 up, 1 down, 3 in a ring around the middle. This one, it matters where I lone pair it. I want to put it on the 120-degree angles, so we get a seesaw shape, which happens to be polar. Polar molecules experience dipole-dipole and London dispersion forces. I wanted the stronger one. I'm circling selenium tetrafluoride. All right, last example. Who has the higher volatility? Volatility is the ability to evaporate. If it evaporates a lot, we're looking for the weaker of the forces. So I'm supposed to draw them, but I don't really need to draw this one. Carbon and hydrogen, all carbon, hydrogen, that's simply London dispersion. It's nonpolar. This one has carbons and hydrogens, but we have an O with an H. They're trying to tell me I have an alcohol group here. OH, alcohol group. It's capable of hydrogen bonding, H-phone, dipole-dipole, and LD. I want the weaker of the forces. C2H6 is the loser, so that's the one that I pick. I hope that helps. Take care.